Hello, Algebra 2 folks. It's time for another little tutorial on function transformations. This time the transformation is referred to as a dilation, or as I like to think of it, the stretch and shrink transformation. And as we do this, we're going to be looking at the same original equation that we used last week, y equals x squared. And we're going to define a function, f of x, that is x squared, and the graph of f of x, what would it look like? Well, that's the parabola. So we know how to graph parabolas, right? Right. Let's see if we go over 3. 3 squared is 9. 6, 7, 8. Whoops. This is 6, 7, 8, 9. Over here, 7, 8, 9. So, bing, just like that. So, what are we going to see on Delta Math today? Let me put in some coordinates here just for fun. 3, 9. Okay, so suppose we see in Delta Math a different equation like y equals 2x squared. Now, you've had some experience with parabolas in the past, and maybe you'd be able to graph that. Of course you'd be able to graph that. What am I thinking? Naturally, you could. But I want to look at this from the point of view of transformations of functions. So the thing to remember here is that we have this function f of x, and f of x is defined as x squared. So this piece on the right-hand side over here has got a 2 times x squared. Well, x squared is also f of x. So this expression on the right-hand side of the equals is also really 2f of x. So just as this black curve here is f of x, what would 2f of x look like? Okay, well, here's how you think about this. Remember, the input to this function is representing the horizontal position, and the output of the function, once you process that input, you get an output. The output is the vertical, or y. Well, that's really ugly. Let me read that again. The y position. All right, so for each one of these points that I plotted on the graph, it has a y position. This one is 0, this is 1, this is 4, this is 9. And so what we're saying is for the same inputs, we're going to take those outputs, or y positions, and multiply them by 2. So let's try that. I'm going to take each of these. Now the one that's at the vertex is at y equals 0. It doesn't change at all because 0 times 2 is 0. The one at 1, 1, it has a y coordinate of 1. 1 times 2 is 2. The next one over 2, 4, its y coordinate is 4. 4 times 2 is 8. And then when it's at 3, 9, its y coordinate is 9. And times 2, that's 18. I'm not plotting that one. So, and on the left-hand side, we're going to get the same thing. Each y coordinate gets multiplied by 2. So I'm transforming these points upward by a factor of 2. And then, of course, I can connect that up. And we have an ugly, but still a parabola. So it's a parabola, and its relationship to the original parent parabola is that it's been stretched vertically by a factor of 2. Every y coordinate on the original graph gets multiplied by 2, and it pulls it out away from the x-axis. The farther out from the x-axis the original point was, the transformed version is going to be twice as far away. So that's a dilation or stretch vertically. All right, let's try a different one. So another type of transformation you might see in delta math would be an equation like this. Now let's not do that. Let's do 1/2 x squared. So inside parentheses, I have 1/2 times x, and that whole thing is squared. Now, what would that look like as a function transformation? Remember, in our original definition of f of x, whatever goes in the parentheses gets squared. Well, here's a thing that in its entirety gets squared. So, working backwards, and backwards is a key idea here, I would write this as f of 1/2 x. So, the contents of the parentheses going into the function, remember that goes into the function, whatever goes into the function gets squared. So this transformation of the parent function is equivalent to this equation. So, question is, what would that graph look like? Okay, well, let's look at this on a feature by feature basis on the original graph. So here's a feature on the original graph. It's at the coordinates 1, 1. I want to know, where does this point on the original graph get transformed to in this situation? Well, this point represents the place where the input to the function was 1. So we need to ask ourselves, what x value would make the input to the function be 1? In other words, how do I make 1/2 x equal 1? Well, that's just a little equation you can solve. X equals 2. So that means when x is equal to 2, and we shove that into the parentheses here, we're going to be figuring out f of 1/2 times 2, or f of 1. And f of 1 is just 1 squared, or 1. So this is going to represent the point 2, 1. So that point that was originally at 1, 1 now is transformed to 2, 1. And I can replot that. And it's going to be a matching one on the other side of the y-axis at negative 2, 1. Got it? All right, let's look at the next point. The next point on the parent function was at 2, 4. That happened when the input to f of x was 2, and you squared that and got 4 as an output. So looking at our transformed case, what do I have to do to x to make the input of the function be 2? In other words, how do I make 1/2 x equal 2? Well, that happens when x equals 4, and that gives us the point 4, 4. So I can plot that one on the graph, and it's going to be a matching one at negative 4, 4. Whoa, okay. So we can do the same thing for the next point, which was at 3, 9. Again, that happened when the input to the function was 3 and we got 9 as an output. So what do I have to make x in this case to make the input to the function be 3? Well, 1/2 x equals 3, x has got to be 6. So that gives us a point at 6, 9 over here and at negative 6, 9 over here. And we can plot that. So yeah, it's a parabola. Now, this parabola, the one that comes from transforming f of 1/2 x, instead of the x coordinates being 1/2 what they originally were, the x coordinates become twice what they originally were. They become the reciprocal of 1/2 times bigger. And that's just so that when you end up multiplying the x's times 1/2, what goes into the function are the same x values that you had in the parent function. So you're really undoing the effect of 1/2. And undoing 1/2 when you're multiplying means this has to be double what it normally is. So, a couple things to note about this. When you got transformations that occur outside the f of x, like this one, we're multiplying the output of f of x times a number, you're going to get effects that are vertical. And that happens if you're adding on the outside as well. You may remember from last week when we added outside f of x, we got vertical translations. Multiplying outside f of x gives you vertical dilations or stretches or shrinks. On the other hand, when we multiply inside the parentheses, we get a seemingly an opposite effect. And it's a horizontal effect. So this is changing where the x-coordinates of the function normally appear. And it's opposite what the effect was when they were outside. On the outside case, if it was 2, you got double. On the inside case, if it's 1/2, you get double. And if this were 2, you'd get 1/2. So the one case that we haven't looked at yet, and I'll sketch that quickly, is say if we're graphing f of 2x, then the x values have to be 1/2 what they usually are in order for the function to behave with the same outputs. So in that case, taking a look at our original points on the parent function, we'd multiply their x-coordinates by 1/2, and we get points like that. So that's cool. Having f of 2x meant that our parabola was shrunken horizontally. It was dilated in a compression effect. And in the case where we had a 1/2 inside the parentheses, we had an expansion horizontally, or a stretch. So what you're going to see when you do some of these delta math exercises is a parent function. You're going to see, well, in this example, you'd see that black curve, y equals x squared, and then you'd be presented with a transformation equation like this. And what I want you to do is think about this in terms of the function. What was the function, x squared in this case, and how would it be transformed? Where does the transformation occur? Is it inside the parentheses or is it on the outside of the parentheses? And how would that cause that dilation to occur? Would it be a vertical dilation or a horizontal dilation? Would it be increasing or would it be shrinking? And to show that in delta math, instead of dragging the green dot, you need to drag the blue dots. And the blue dots are used to express that horizontal or vertical dilation. Well, I think that's it. So go try that out. Good luck. Have some fun.